right. Hello, everyone. Welcome back to Math 162, Week 4, Lecture 2. This is our 8th meeting together for the summer. Per usual, just going to take a minute, talk about our, quote, whiteboard, including homeworks and upcoming tests. So 5.5 and 5.6 due today. No surprises there. We finished 5.7 last time, so that is due on the 22nd. We will finish 5.8 today, which means that that is due on the 24th, a week from today. It also means that we will have finished all of the Chapter 5 material, which is what the test covers. So as discussed last time, the test, you will have 2 days to take it at your leisure in my math lab under the quizzes and tests section. It's 25 questions, 2 hours long. You will need to show your work, number your work, put your name on your papers, then take pictures or scan them and submit that within Canvas within 15 minutes of finishing your test. I will cross-reference those times. The work submission is also due the same time, although if you turned it in at like 12:10 a.m. or something on the 26th, it would accept it. It would be fine. I'm not going to count that as late, obviously, because you're still within the 15-minute deadline. And then if you have any problems where you got them wrong, but you think your work deserves partial credit, then you shoot me an email and say, hey, Mr. Beckner, check out questions 14 and 21. I think I can get some partial credit on that. You can explain why if you like, or you can leave me to do the deductions from there. It's up to you. And then I will check it out and get back to you. Per usual, if you don't hear from me within 24 hours, just give me a bump in the email and say, hey, Mr. Beckner, what's the status? Unless it's the weekend, remember, wait till Monday for that, because the weekend doesn't count as a business day. You turn it in, you'll be turning your work in Canvas. You will not see the location to submit it until the 2 days the test is available, but it'll be under the main screen. You have the lecture videos at the top, and you have your formula sheet, and then it'll be right under that or above that, but you won't be able to miss it, I promise. There is a review assignment located in the homework. It's directly under the 5.8 homework. It says either test 1 review or chapter 5 review, something like that. That is not an assignment that you have to complete, but I highly, highly, highly suggest it because the test parallels the review material. Please remember, this is a no notes, no books, no calculator test. So when you take your test, it's supposed to be you're starting out with a blank piece of paper, and then you can go from there. Remember to answer your questions analytically. So something like if your answer is the square root of 2, if you write 1.4, if you rounded it, which it wouldn't even say to round anywhere, that would be wrong. And I would highly, highly, highly suspect you've been using a calculator at that point and bad things happen, which we do not want to happen. So do not use your calculators. Remember, we've talked about a lot of things that you should just know off the top of your head, and that should last the whole semester. Things like that the tangent is sine over cosine isn't going away. Your quadrantal angles are not going away. You're a smart trig class. That's not going to go away. All of that stuff is going to stay with us while we are doing trigonometry, which will last the entire semester, except maybe like the last week and a half, where we switch gears just a little bit. But even still, when you go into calculus, you're going to have a lot of this trigonometry stuff memorized. There will be things that aren't as big of a deal, of course, to have memorized. You can just kind of regather those thoughts and ideas along the way. But SOHCAHTOA, oh, if you don't have that memorized in calculus, you're going to be in trouble eventually. It's not that everything in calculus involves trig, but you will do some calculus with trig. But I don't want to take too much more of your time. Oh, I do have one more thing to announce. I forgot to put this up here because I had literally 0 seconds between classes. The day of the 24th, actually, the day our test starts, I'm not going to be able to hold class live that day. I have something going on that could not be rescheduled. So I will not be holding class live. However, that does not mean we won't have class. So on 6/24, class will not be held on Zoom. I will pre-record everything and have it in YouTube before class starts. Most likely I'll have it available on the 23rd, but worst case scenario, I will be putting it up on the 24th. So you know how when you go in Canvas, the very top link is the live lecture link, and then below that is all the previous classes. On the 24th, the very bottom one at the time, you will already see the class for the 24th. So please understand, you are responsible for watching this on your own time. You can watch it on the 24th or the 25th or the 26th. Just watch it before the next class. Which would be, what's that, the 29th? Yeah, the 29th. So again, the only thing is you won't have me to answer questions in the chat while we're doing our lecture like we normally do. But if you have any questions, you can always email me. I answer all emails. I answer all questions, just like I do in class. So I hope that this will be a non-issue. And hopefully it doesn't have to happen again. So again, on the 24th, class will not be held live. I will even change the Zoom link to say no live class today. Check the recording in YouTube. It'll probably be ready on the 23rd, but this will be a great opportunity. So that way, if you absolutely wanted to take the test during our class time, there you go. You don't even have to worry about missing the live lecture. It doesn't exist. It will already have been recorded. And yeah. So we're going to pick up where we left off now with 5.8. We will complete 5.8 as well as start 6.1 by the end of class. I am going to have one weird edit to do. I have a small portion to skip just because of technological issues when I was recording. Stuff happens, right? But anyways, let's go ahead and get 5.8. Applications, everybody's favorite.
Which is applications. Just make that title just a little bigger. There we go. All right, so I just want to make a couple statements about the inverse trig functions before you actually get in the applications, and that is because there might be a time with an application problem where you need to know these facts. So as a reminder, these are reminders. If you have y equals sine of theta, that's the same thing as saying theta is equal to the inverse sine of y. But your theta must be between negative pi over 2 and pi over 2. Then we said if you have y equals cosine of theta, that means it's the same thing as saying theta equals the inverse cosine of y. But with inverse cosine functions, the theta must be between 0 and pi. And then we had if y equals tangent of theta, then theta is the inverse tangent of y. Where your angle is like sine, it must be between negative pi over 2 and pi over 2. So maybe when you're doing an application problem, you get this equation y equals, or maybe you have a number over here, it's 13 equals sine of theta. And you're supposed to be finding the angle. Well, you can find the angle by doing the inverse sine. But you have to make sure that your application problem, if your angle was in quadrant 2, for instance, and you're doing an inverse sine, it's going to spit out, your calculator is going to spit out an answer that's not in quadrant 2, it's going to be in quadrant 1, so you would have to know to transpose that angle to quadrant 1. So again, these ideas are important for applications where you have the sine of the angle, cosine of the angle, or tangent of angle equal to that ratio. So you know you have to do that the angle is the inverse trig function, but you also have to know where those angles are valid because your calculator is going to only give you answers in these windows. However, for an application, your angle could have certainly been in one of the other two quadrants. The inverse trig function is invalid. So you have to use the answer from your calculator as a reference angle and then put it in the correct quadrant. So you might have an angle that's supposed to be in quadrant 2, you use an inverse sine, and the calculator says, oh, it's in quadrant 1. But you know, well, no, I know when I drew up the picture, the angle was in quadrant 2, so I have to use what my calculator told me as a reference angle. This is when things get really complicated. I will mention that the applications we're going to be doing together, this won't even be valid. So this memo at the bottom, which I'll just type up, right triangle. Why is my font still so small? Problems. The angle and its quadrants aren't an issue because quadrant 1 is always valid in the inverse trig functions. There we go, a little better. All right, so let's just get down to brass tacks. Example 1. Complete triangle. I'm going to give you a right triangle. And I'm going to tell you that this angle right here is 34.5 degrees. I'm going to tell you that this distance right here is 125. I'm sorry, that's not right. I'm looking at a later example. The 34.5 is right though. It's 10.5. And that's it. That's all I'm giving you. So I'm asking you to complete the triangle. So what I'm asking you for is, well, if I want to label all the sides, let's label this as angle A. We'll call this angle C. I wish I had put my triangle a little. Shoot. Do it this way. Copy paste. There we go. There we go. There we go. And then I'm going to call this angle B. So we tend to use capital letters for angles. So this is a capital C. This is a capital C. We tend to use lowercase letters for side links. So uppercase letters for angles, lowercase letters for sides. Now I labeled this as angle A, and you can see it's 34.5. So I'll call the C the hypotenuse per usual. So this is going to be a lowercase c. Maybe I'll even make that other one a much more exaggerated C. Please, thank you. And then the legs would be your A and your B. It doesn't matter which one you call which normally, but since I called this angle A, in trigonometry, we have to make these the same, so the side opposite has to be the lowercase a. So again, because I made this an uppercase A here, the side opposite of it has to be the lowercase. Because I made this an uppercase B, the side opposite where the 10.5 is has to be the lowercase b. Because this was angle C, which is 90 degrees, this has to be the lowercase c. So we know angle A, we know angle C, but not angle B. We know side length B, but not A and C. So there are three things we have, and there are three things that are missing. This is a pretty common triangle problem. And we are going to keep doing this type of problem as the semester progresses, but in more complicated ways. Right now, we are basing everything off the fact that we have to have a right angle. Eventually, we won't. And that's going to be awesome, but it complicates things. All right, well, the easiest thing to find first would be angle B. Angle B, well, we know that the sum of the interior angles of a triangle is 180 degrees. So angle B should be 180 minus the other two. Should be 180 degrees minus angle A minus angle C, which is 180 degrees minus angle A was the 34.5 degrees, and then angle C was the right angle of 90 degrees. And when you do that subtraction, you will get 55.5 degrees. So that's angle B. Now we have all three of the angles. That's the easiest thing to do. When you know two of the angles, the third one just falls in place because we know the sum of the interior angles of a triangle is 180 degrees. If you don't know that, you were just retaught it. And please don't ever forget it again. All right, so we got B, so that one's done. The only thing we're left to find now are these links A and C. And you might go, oh, Pythagorean it. Well, Pythagorean, the a squared plus b squared equals c squared only works if you know two of the three. All we know so far is one of them. So Pythagorean's not going to work yet. We can certainly use it later, and we might. But for now, what we got to think about is, all right, we know these two angles and we know this length. We can choose to find A first, or we can choose to find C first. No one cares. I'm going to choose to find A first. So I'm going to go after A first. And I can't just say A equals blah, blah, blah. We're going to have to do some trigonometry and some algebra. So the basic idea, and this was something we also reiterated at the very end of last class a week ago, is as long as you know two of three things, you can find the third thing. So we have an angle, and let's just go with the angle A since B is one we found. So we know 34.5 degrees. We have its adjacent side, and we want to know its opposite side. So we've got to think about what trig function uses an angle, the opposite, and the adjacent. Well, tangent and cotangent. But don't use cotangent, use tangent because it's easier. All right, so we will say that the tangent, and I'm talking about this one, so the A is the opposite, the B is the adjacent. You could still use angle B of 55.5 degrees, everything's just upside down. So the tangent of 34.5 degrees would be its opposite of A over its adjacent of B, but we know B is 10.5. Well, all you do is multiply both sides of this by 10.5 to solve for A. So we take 10.5 times the left side and 10.5 times the right side. Sorry, I got to squeeze that in a little bit. We do that so that the denominator clears. So now this just says that 10.5 times the tangent of 34.5 degrees is equal to A, which we can just put this in a calculator. Now, I usually give a no calculator test for test one. And so far that is still true. If I give an application where I feel like the calculator is necessary, I'll let you know ahead of time, hey, for one question, for the word problem, you'll need to pull out a calculator. So once I create the test by next class on Monday, you'll have that information, but I still have to build the test. The events of, well, it was pretty much an all weekend thing in Monday and Tuesday, have kept me insanely busy, so I haven't made our test yet. So yeah, calculator, that's all we're doing. Pull out a calculator. If this was a no calculator test, this would be the answer. And I would probably have to go and input your points for that manually, which wouldn't be a problem since there's only 10 students. All right, so we just do everything first, right? Nope, we check our mode. And I'm in radians, where I'm gonna be typing in degrees, so that's a problem. So we gotta switch our mode to degrees. Get out of that menu with second quit, and just type 10.5 times the tangent. You can hit times if you feel like you need to, but for my calculator, I don't. And then 34.5 degrees, close our parentheses. And we end up with 7.2 blah, blah, blah. I did not say to round to one decimal, but that's what we're gonna round. So we're just gonna say this is 7.2. So that's this length. We now know the two legs, which means we can find the third side by Pythagorean. Alternatively, if you wanted to use another trig function, what you could do is say, all right, well, we know the angle, we know the adjacent side, we now also know the opposite side, so we could find the hypotenuse by using the sine or the cosine function. If you use cosine, you'd be going with the adjacent, which is the 10.5, so you'd go 10.5 over c equals sine of 34.5, or if you wanted to do, I think I said sine, I meant to say cosine, 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 cosine. Or if you wanted to use this information from A, you'd say the sine of the angle is A over C. And then you would do pretty much the same thing we just did in the last one. But most people, once they can do Pythagorean, they go ahead to Pythagorean. So let's use A squared plus B squared equals C squared to get the C now. So we know that 10.5 squared plus 7.2 squared would be equal to C squared. Just take the square root of both sides. So that says that C is equal to the square root of 10.5 squared plus 7.2 squared, which if you plug that in a calculator, big square root, 10.5 squared plus 7.2 squared, parentheses, and we get 12.7 when we round to one decimal. So there are our three unknowns. We found the missing angle of capital B, and we found the leg and hypotenuse, what we called A and C. What you call these letters is completely arbitrary unless the example in my math lab already defines them, and then you got to make sure you're putting them in the correct spots. All right, let's try another. Example 2, same thing. We're going to complete the triangle. Actually, no, we're not going to complete the triangle. We are just going to find the important bit of information. So I'm going to make another right triangle. These are not being drawn to scale. Please don't think that they are. We're going to have this be 57.2 degrees. We know the horizontal distance, we saw this number earlier, 125. And I want to know, what is the height here? So that distance is what I'm going to call A. I don't want to know the hypotenuse. I don't want to know the other angle. I'm the boss. I ask you, the employee, to go out and you stand 125 feet away from a building. You get your electronic device to be able to measure that from your position on the ground to the top of the building, it's 57.2 degrees. And I'm asking you to confirm the height of the building. Maybe one contractor said it was this height. Maybe one contractor said it's 200 feet tall. Maybe another contractor said it's 194 feet tall. And I'm asking you, well, which one was right? Who did the wrong math? Who do I got to fire, or who do I not want to rehire? You know, that kind of thing. So you stood 125 feet, away from the building. You got your electronic device that measured 57.2 degrees to the top, and you're going to confirm the height with very basic trigonometry. So you have your angle, you have the adjacent side, and you're wondering what the opposite side is. So you ask yourself, well, self, what trig function uses opposite and adjacent? Well, we just said it last time, tangent. So we're going to say that the tangent of 57.2 degrees is equal to its opposite over its adjacent. Its opposite we've called A. Its adjacent was given to us as 125. You're going to multiply both sides by 125. To isolate the variable, so that the 125 is on the right cancel. If your variable's in the bottom, you'd be multiplying both sides by the variable. You got to get rid of the fraction part. And what this tells us is that 125 times the tangent of 57.2 degrees is equal to A, which we can just stuff in a calculator if we need the approximation to one decimal place. So 125 times the tangent of 57.2. I already put myself in degrees earlier, so I know I'm still in degrees. I trust myself. And we get 193.96 blah, 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 which rounded to the nearest tenth would take the sixths to round up, so that 9 becomes a 10. So even rounding to the nearest tenth, we round this to 194. So I gave you two options earlier. I said contractor A said it's 200, contractor B said it's 194. So contractor A is fired because he was wrong. Maybe not fired, maybe scrutinized more, I don't know, but you get what I'm saying, I hope. Now, a similar example, let's say you were more interested in this angle, kind of like that physical therapy problem I did at the end of last week. So maybe you have the problem this way. Maybe you know this distance is 125 feet. Maybe you know this distance is 194 feet, and you don't trust your measuring device, and you're wondering what this angle theta is. So maybe your measuring device said it was 57.2, and maybe Bob's measuring device said it was 56.9, and you're wondering which one is more accurate. So you'd go, okay, which trig function uses opposite and adjacent? Well, it's still tangent. So you'd say the tangent of your angle is equal to 194 over 125. And this type of problem is what I was referring to at the very beginning. We have a tangent of an angle equals some number. But the thing we need to know is the angle. It's not solved for here, so we have to do this instead. And we don't know any particular right triangles where this would be a known angle. So what we do is we turn this into theta equals the inverse tangent of 194 over 125. So we pull out our calculator. Now this was a right triangle problem. All our angles are from 0 to 90. So all of that, it's between this angle and that angle will be irrelevant for us. It's easier. So we just do second tangent, 194 divided by 125. Close it, see what we get. And we get 57.2. So the other person's measuring device that said 56.9 is now going to be calibrated or maybe just thrown in the trash. So theta is 57.2, and that's degrees. We made sure we were in mode. These problems where we might have to worry about the angle, again, you might have one, I think one in the homework, and that's it. I'm not going to do that on the test, though. Yeah. Okay. That was example 2, even with a extra little sidebar. I just want to write here similar but different. Because this was me giving you a different value. Instead of giving you the angle and a side, I gave you 2 sides. That's how you would have to find the angle. If I gave you the opposite and the hypotenuse, you'd want to use inverse sine. If I gave you the adjacent and the hypotenuse, you'd want to use inverse cosine. How do you know? Because that's what those trig functions deal with. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. All right, example 3. In this example 3, we are going to see text example 4. So I'm actually going to pull up the textbook. I also want to pull up another blank file so I don't show too much stuff. I don't want to give you all the work and the answers and stuff. So I got my textbook loaded, hopefully still. Yes, I do. And then we'll do this. There we go. Do I need to scroll down just a touch? No, that was good enough. Don't look, don't look, don't look. Close your eyes. Okay, you can open your eyes. All right, so example 4, you are taking your first hot air balloon ride. Very awesome. Always do that at least once unless you're terrified of heights, in which case you do you. Your friend is standing on level ground 100 feet away from your point of launch. So you can see the diagram to the left. We got our hot air balloon here, and then the basket's on the ground initially. And the balloon would be on the ground initially too before it fills up with air, but we don't need to get too crazy with this. So your friend's standing 100 feet away. So 100 feet away from where you were standing in the basket when you first started the launching process. And he's making a video of the terrified look on your rapidly ascending faces. Don't you love that? How rapidly though? How rapidly are you ascending? So we're not going to treat this as a calculus problem, but we're kind of setting it up as one. At one instant, the angle of elevation from the video camera to your face is 31.7 degrees. So here's your friend, and his eye was level to your eye. You're the same height. And where he's holding the video camera, the angle up to your eye in there, we're kind of like neglecting the fact that we're about 6 feet tall. We're just saying there's 6 feet of spacing here, but they're on both sides, so it's irrelevant. So originally, when you start going up, the angle is 31.7 degrees, and you've got some height A. Then a minute later, so you apply your hot air. It fills up with hotter air, and it causes it to rise due to pressure in heat, and all that stuff being an inverse relationship. Blah blah blah. Anyways, so a minute later, now you're way up here, and the angle that the camera that you can measure is 76.2 degrees. So at maybe 2 minutes in, 31.7 degrees, and then 3 minutes in, which is 1 minute later, it's 76.2 degrees. So we picked up speed. It's very clear that we picked up speed. So they want to know, how far did you travel to the nearest tenth of a foot during that minute? During that minute. So they are saying they want to know, all right, at the start of that 1 minute, you're here. At the end of that 1 minute, you're here. They want to know what is this height, and I'm going to call it x. Now that is not the entire length of that larger triangle. It's not the length of the shorter triangle either. That length is the difference of those two things. So what we're going to have to do is find A first, then find B. I think we can actually find them interchangeably. And by think, I mean I know we can, but we'll do the smaller than the bigger one. So we'll find A, we'll find B, and then we'll just say that x is the difference of B and A. That's a very basic concept. At this length, if the total thing is B, if A makes up this portion, x would be the difference of the two things. Because A plus x is B, that means B minus x is A, or B minus A is x, either way you like to do it. So that's going to be important issue 1 with this problem. So I'm going to redraw this triangle. Then I'm also going to draw them as their own triangles. And let me clear my screen, come off of annotate, and let's pull up our actual. Okay. So we had big picture, and then we had a smaller triangle inside of it. So for the smaller one, this was, I believe, 31.7 degrees, if I wrote everything down right. And then for the larger one, it was 76.2 degrees. Oh, I forgot to do this. That's the 31.7, and it's going to look a little exaggerated, but this is the 76.2 degrees. Now we had the height, and we didn't say exactly how long our flight was at this point. We had some height, maybe 5 minutes in, maybe 10 minutes in, I don't know. So A would be the height there. And then B, we said, was the height of the entire thing. B was going from here to here. And then we called X the distance from here to here. That's what we actually want to find, X being the difference of B and A. This is a lot of information all at once. Here's my first suggestion. Draw these as separate triangles. So let's make 2 triangles. Let's do the blue one by itself. That's terrible looking. Let's try it again. Where this is 31.7 degrees. I also forgot to write the 100 feet on the bottom. That was the horizontal distance. So this is still 100. And then this would be A. And then for the bigger triangle, I'll do in red. I'll do red for the bigger triangle. So that was a larger angle. I'll try and make that visible. That was 76.2 degrees. This was still 100 though. And we called this distance B. So what we got to do is we got to find A from the blue triangle. We got to find B from the red triangle. And then our number is actually just the difference of those two things. So for the blue one, all right, we got an opposite and an adjacent. We don't actually have the opposite, but that's what we need. So angle, opposite, adjacent, we're going to use tangent again. The tangent of 31.7 degrees would be equal to the opposite over the adjacent, A over 100. Same thing as before, multiply both sides by 100, you get 100. Tangent of 31.7 degrees equals A, and you can put that in a calculator, which we will do right now. I almost wonder if y'all just heard my stomach growl. I'm very hungry and had to skip lunch because my classes ran over. 100 times the tangent, 31.7. 7, I know I clicked it, here we go. And we're gonna hit enter. And what we come up with is 61.7 blah, blah, blah. Let's keep this to rounding to the nearest tenth, which will be 61.8. So 61.8 is equal to A. And let's put the units as what they should be. We're talking about feet, so it's 61.8 feet would be equal to A. Now let's do the same thing for the red triangle. So A was the height whenever we started the clock, 4 or 5 minutes in. I don't even know. We don't have to worry about that particular detail. B is the height 1 minute after that initial height. So yes, we started on the ground. After maybe 5 minutes, we were 61.8 feet in the air. Then another minute passes. Now we're wondering how high are we now? All right, so opposite, adjacent, it's tangent again. So the tangent of 76.2 degrees is equal to b over 100. So we're going to multiply both sides by 100. That way we can solve. So we have 100 tangent of 76.2 degrees is equal to b. Then we're going to stuff that in our calculators, which, come on, pull up. So we'll do 100 tangent of 76.2. We'll close it for good measure. And we get 407.1 feet, 407.1. So 407.1 feet. That is how high we were after that one more minute. Man, we managed to fly quite a distance in that 1 minute. So maybe we weren't 61.8 feet in the air 5 minutes in, maybe that was 5 seconds in. Well, if you actually knew how hot air balloons kind of ascend, they do ascend very slowly at first and then quicker and quicker. So this could have been 5 minutes in and then, all right, we've picked up speed. Okay, so what was the point of this? We wanted to know what was the distance we traveled in that 1 minute, which was the difference of those B's and A's. So X would be B minus A, which we said is the 407.1 feet minus the 61.8 feet. And when you do that, what is that, 345.3? Yes, it is, 345.3 feet. That is how far that hot air balloon traveled in 1 minute. This is one of my favorite types of problems. I love this problem because it makes you think big picture. You've got a small picture to worry about, small picture to worry about, then big picture. You have a calculation to do outside of just doing trigonometry on 1 or 2 triangles. You have to think about everything. You have to put the pieces of the puzzle together. All right. So with that being said, do I want to do... I got one more example. Well, 2 more actually. I need bearings for it anyways. Okay. I was thinking if I wanted to do bearings last, but I did give an example that uses it, so I need to describe it. All right. Bearings, small font again. So in this course, we have said that you always measure your angle for traditional angles from the positive x-axis. If we're doing a reference angle, either the positive or the negative x-axis, but never the y-axis. Bearings are the opposite of that. Bearings feel like you're measuring from the y-axis, or either positive or negative. So the way this works is, start in the first direction, C. Move X number of degrees towards the other direction described. A bearing is something like, I don't know, north 50 degrees east or south 14 degrees west. That's a bearing. So bearings are very often used for ships, for sailing. So because you're just thinking about, all right, well, I'm going based off of north or based off of south. So they call it a north-south bearing, and that's actually one of the homework questions. I'm just spoiling that. It's one drop-down menu is north, one south. That's it. So bearings are measured north-south. So it goes north, then an angle, and then east, or south, and then an angle, and east or west. So when they say that bearings are measured from on north-south, they're saying that you start that whole phrase with north or south. And then the second part is either east or west. What exactly am I talking about in case that was too much? Example, what are we up to? 4. Draw angle described. A weird when it does that to me, but whatever. We're going to have north 18 degrees west. So I want you to draw this angle. Well, I hope you all know that north would be here, east would be here, south would be here, and west would be here. Instead of just x and y, these are no longer x-y axes. These are north, south, east, west, weather vane kind of things. So we're supposed to be drawing the angle north 18 degrees west. So north by 18 west is how some people like to phrase it. North by 18 west. So that says we're thinking about, all right, we're heading in a northern direction. So we're either heading northern or south. So we're heading in a northern direction, but then we're going to go 18 degrees towards west. If I said in 18 east, I would go 18 degrees towards the east. So this angle would look something like this, and the 18 degrees is right there. Again, this is absolutely completely different from any way we have measured an angle ever in this course up until now. Bearings are completely different from traditional trigonometric angles. But in the real world, a lot of people talk about bearings, so it's an important thing to discuss. Now, what the homework tends to do is the exact opposite. They tend to show you the angle, but they would give you, all right, they'd say this is what, 72 degrees? They'd give you the blue and say, what is the bearing? And you'd have to figure out the black ink that I wrote. It's north 18 west, because you'd have to figure out, well, this is 18, and then that's north and west. But you can do it either way. It's not really a complicated problem. It's just getting used to the notation, that it goes letter, number, letter. And I'll even admit, if I don't do bearings for a year, I always want to go the number and then the 2 letters. So 18 degrees northwest is the way I think in my head. So again, if I don't do this for a long time, I get the notation wrong. But I also have the ability to look at it once and then remember it for a year, which is what we like. It's okay to forget things as long as you can very, very quickly pick them up again. All right, B, let's do south 81 degrees west. So we draw this up, east, north, south, west. Crummy looking in. So we're going south by west. So our angle, instead of pointing up, we're going to be pointing it down. So maybe it's here, maybe it's here, maybe it's here, maybe it's here. It's one of those 4, basically. But it would not be one of any of these. So we're going south, and then the next letter is west. So we are not going to swing this way. That would be swinging towards east. We're going to swing towards west. And we got to swing 81 degrees, which is quite a bit. So this would be our 81-degree angle, which would make the more normalized trigonometric reference angle of 9 degrees, or the true trigonometric angle of, what's that, 189 degrees. But as a bearing, it's south by 81 west. Or 81 degrees south by west. I mean, I don't care how you say it. Outside of this class, I don't care how you write it. I don't deal with bearings a lot. Which, if I don't teach a trigonometry class for a year, that's the scenario I literally described. A lot of teachers want to make you think that they absolutely know everything and remember it forever. And they're full of something I won't say on a recording. Some of them are geniuses. But most teachers are just adaptable, and they can not see something for 4 or 5 years, come back to it having forgotten a little bit, but remember what it is, re-pick it up, and still be able to communicate it effectively. All right, so Next, we're going to do example 6 from the text now that we have bearings in mind. So bear that in mind. I am so sorry for that pun. I'm not actually, but I like to pretend. Example 6, here we go. And again, let's try not to spoil too much of the fun. So let's get our cover up. Here we go. A boat leaves the entrance to a harbor and travels 25 miles on a bearing of north 42 degrees east, or north by east 42 degrees, or north 42 degrees by east, however you want to say that. The figure shows that. So we're on a bearing north 42 east. So here's the harbor entrance, and we're heading out this way. So this is the direction we're initially heading. So this is us initially. So we're going north by east 42 degrees. So that means we're going mostly north, but then swinging 42 degrees towards east, not west. So we go, and then something happens. The captain turns the boat 90 degrees clockwise after a while and travels 18 miles. So we traveled 25 miles where this red ink is that I currently have, and I'm about to put more red down. And then you make a 90-degree turn. So here's our 90-degree turn. And they say we turn clockwise. So that's why we went. So this was where we would have continued going, but then we turn 90 degrees towards clockwise. So that was our turn. If we'd gone counterclockwise, we'd be going in this direction instead. Undo, 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 undo. There we go. Okay. So then we travel 18 miles. Here's our boat now. So you are here. And they even tell us that that bearing was south 48 degrees 18. So here's your north-south line. And on that, we're traveling south, so south, and then but south towards east, so it's pointing that way instead of left. So this was north and east, then south and east. First of all, they want to know how far is the boat to the nearest tenth of a mile from the harbor entrance. So the first thing they want to know is, what is C? What is the hypotenuse of that right triangle? So it's a good thing our captain made a right turn, because otherwise we wouldn't know how to find this yet. We'll need a later chapter for it, but we will get there eventually, of course. So we want to find that distance first. Then the second question is, what is the bearing to the nearest tenth of a degree of the boat from the harbor entrance? So the last thing they're going to want us to know is, what is this angle? So just from the harbor entrance to our current position, what bearing is that? And you can see that it's going to be a northeast bearing, because from here we're going north and east. So those are the two things that we need. Let's see, I'm gonna do this. Let's do, sorry about that extra little scribble there. It's gonna be there for a few minutes. So we said example 5. Let's just see the text. Example 6. Let me just, how far is the boat to the nearest tenth of a mile? How far is the boat to the nearest tenth of a mile? So A, how far is the boat from the harbor? Which means we're finding that C over there. So I'm just going to draw up the triangle. So we know this was a right angle. We know this will be the angle we need to find eventually. And we need to find C for now. We know this distance was 25 miles. We know this distance was 18 miles. First thing we're going to do is find C. So C equals, well, that's a right triangle, so A squared plus B squared. 25 squared, sorry, C squared equals 25 squared plus 18 squared. So C would be the square root of that. That's an ugly square, isn't it? Let's try again. There we go. Which one we round to the nearest tenth? Let's pull out our calculator. We're doing big old square root of 25 squared. That was not a square root. Let's start over. Big old square root, 25 squared plus 18 squared. And we get 30.8. Rounded to the nearest tenth, so that would be 30.8 miles. So yeah, we went 25 miles this way, we went 18 miles that way. So our boat, in terms of fuel consumption and actually how far it traveled, we went 43 miles. We have moved 43 miles. But in terms of from our original position, if you just wanted to take a straight path, so maybe we were broke down and someone's got to scoop us up, then that boat that's got to scoop us up is going to have to travel 30.8 miles. They don't care that we went 25 miles this way and 18 miles that way. They're not going to be putting 43 miles in our boat and traveling the same path. They're just going to say, we know your position. We're heading directly towards you because we're not going to waste fuel. For part B, they wanted to know what was the bearing from the harbor. Now I drew this as a flat. It was a little crooked over here. Don't worry about that. This is good enough for government work, just not drawn a scale. Well, here's our angle. We have the 3 different links here, but we approximated C, so I would try not to use C. So I would say it's probably a good idea to use tangent again. So we'll say that the tangent of our angle is going to be equal to its opposite. Now, this is drawn differently than how we usually draw our triangles, but that's okay. The opposite is the 18, the adjacent is the 25. So we go, tangent of the angle is 18 over 25. But in order to solve for the angle, because it's inside, that means you need to go to the inverse tan function. Now, if this was a square root of 3 over 2, or a half, or a square root of 2 over 2, then you know it's a 30 or 45 or 60 degree angle. But that's not the case here. So theta would be inverse tangent of 18 over 25. So we'll stuff that in our calculator. Inverse tangent of 18 divided by 25. And we get 35.8 degrees when rounded to the nearest tenth. 35.8 degrees when rounded to the nearest tenth. But is this a bearing? No, that was supposed to be a question mark. It's not. It's not a bearing. That is absolutely not a bearing. That's a traditional angle because that's measured from a horizontal positioning. So what we actually have to find is the bearing. So if we were going, let me put my annotate back on. So this theta we know is 35.8 degrees. The actual angle we are trying to find is this. This is the bearing angle because we got to go from north to east or west if that's how it was positioned. So this is just basic arithmetic. We know the angle here was 35.8 degrees. We know this angle is 42 degrees. Well, we swing 42, then we swing 35.8. So that whole angle would actually just be the sum of them. So our angle, oops, let me not do it that way. Off of annotate, there we go. So our angle would be the 42 degrees plus the 35.8 degrees, which when you add those up, you will get 77.8 degrees. That is not the, if you just wrote this, that would not be it. That's not a bearing. Bearing itself has to throw the north, the south, the east, the west, that stuff into it. So we're going in a north direction, but also an east direction. Don't go east then north. It has to go north, then east with the angle in between. That is the bearing that our rescue ship would have. Humana, what do we got? 15 minutes. Let's do another. Now I don't need the textbook anymore, so I will maximize this. And I need to clear my annotations so that that's not sitting up there. All right. Last example of the section, example 6. You're flying a kite, you know the length, string, the 80 feet. How do you know? You extended it and you measured it. And observes that when taut, not as in teaching, as in a tight string, it forms a 22-degree angle elevation. Angle of elevation is the traditional angle we've been using, not a bearing. And that's when the handle is on the ground. So not from 4 or 5 feet up, however high we're handling it. We're going to put the handle on the ground so we can keep things clear and precise. How high is the kite? So it would be very difficult unless we're flying this kite right next to a building and we put someone in the window and they measure how high up they are, by dropping a measuring tape or something like that. These would be a lot easier things to measure. The 80 feet of string you can do on the ground. The 22-degree angle, you can get a caliper or just any boring device that measures angles. Doesn't even have to be a digital crazy caliper to measure 22 degrees. We didn't go to the nearest 10th or 100 or anything like that. We can just get a protractor. So picture's worth 1,000 words, right? Let's draw it up. So we're standing here. So we're here on the left. So this is us. This is you, if you will. And then we're flying a kite, and the length of the string is known to be 80 feet. And your friend measures a 22-degree angle. 22 degrees is kind of small, so we'll make this kind of small. So this right here is where the kite is. And this is our 22-degree angle. So we know we're going to have a right angle here if we just drop it directly down. Now we know that the length of string of the kite when fully extended is 80 feet. Is this the 80? No, that's definitely not the kite string. That's the height off the ground. Is this the 80? No, that's the distance from you to directly under the kite, but that's not the string. The string is the hypotenuse of this right triangle. This is the 80 feet. And the thing that we want to know is the height of the kite, which would be this vertical distance right here. You could call it X, you could call it B or A. I'm going to go H for height. All right, so we got a right triangle with an angle, a known hypotenuse, and an unknown opposite. Which trig function uses an opposite and a hypotenuse? The sine. So we'll say the sine of 22 degrees is equal to its opposite of H over its hypotenuse of 80 feet. You're going to multiply both sides by 80 to clear the denominator. So you get 80 times the sine of 22 degrees is equal to H, which we can stuff in a calculator and round to the nearest tenth. 80. Sine of 22 degrees. Make sure you're still in degrees if you have to. If you're paranoid, check it. And we get 29.96, which we round to the nearest tenth. The 6 rounds the 9 up to a 10, so the 29 rounds up to a 30 feet. There we go. Kite's 30 feet up in the air, about 3 stories high if you say a story is 10 feet. It's not always true. Depends on the building, but it's kind of the average. Alrighty, that will close out 5.8, which was applications. Did it write 5.8 at the top? Yes, I did.
Quick edit.
And this is 6.1, verifying trigonometric identities. center. Move left. Get lots and 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 lots of space. Okay. So verifying trig identities. Trig identities are equations that you must make the left and right side match. We'll do this by using various trig properties seen in the last chapter. An identity is only verified once the sides match. Example. Sine squared of theta plus cosine squared of theta equals 1, while true is not verified. So if this is a handwritten problem, if this is where you stop, oh, okay, well, yeah, sine squared plus cosine squared is absolutely the one. That's the base Pythagorean identity. But you did not technically show me that it's done. You would have to show the match. So you'd go from this. You'd go from sine squared of theta plus cosine squared of theta equals 1. And then you say, oh, well, sine squared plus cosine squared is 1. So then you just say 1 equals 1. And then you're done. It's only then that you're done. It is only then that you are done. Now, your homeworks, they're basically just going to ask you for a couple steps along the way, or maybe what property you would use to simplify things. So it's not the end-all, be-all, unfortunately. So the way I'm going to be doing my examples is, and we are going to do a whole boatload of these so you can see lots of variety and lots of variability and complexity. So while in the homework and maybe in the test, this isn't how things are going to be done exactly, you still need to be able to follow and replicate what I'm doing, because these trig identities are important for using things down the line. When you have a calculus problem, your calculus problem may be in, say, secant squared, and you don't have a formula for secant squared, so you need to turn it into something involving tangent squared, which you might have a formula for. So how do we do this? I just mentioned that it's by doing all the various trig properties we've already seen, as well as some algebra tricks and tips. So here's some basic tips that generally work. First of all, turn everything into sines, and cosines. So if you have a tangent, turn it into sine over cosine. If you have a secant, turn it into 1 over cosine. I'm not saying you have to. I'm saying these are tips that generally work. I'm not saying you have to do any of these things. And I want to have this bolded. Next tip is to use your Pythagorean identities. The fact that sine squared plus cosine squared is equal to 1, or 1 plus tangent squared is secant squared, or 1 plus cotangent squared is cosecant squared. Those 3 things can be helpful. Which are, again, I said them, but I'll write them down. Sine squared of an angle plus cosine squared of an angle is equal to 1. Then the second one is tangent squared plus 1 is equal to secant squared. And the third one is that 1 plus cotangent squared is equal to cosecant squared. You'll notice that very often moving forward, I won't always say cosecant squared of the angle or cosecant squared of theta. I'll just say cosecant squared. Please understand you still have to write those angles. It's just most people tend to skip saying them when you have to write it 50 times. So those were your Pythagorean identities. as a fresh reminder. So another thing that is helpful is to factor a GCF out. If you notice that there's a GCF or maybe a difference of squares or a trinomial, that you can use the shortcut method or the AC method or trial and error or the box method or whatever method you've learned. Please understand, I am not here to teach factoring. I will not teach factoring. That's what Pre-Calc 1 was for. You were supposed to have mastered it then. If you have not mastered, go and do 500 of them this semester and master them, because you will be factoring things that aren't going to just be x squared minus 9. You're going to be factoring things that look like sine squared minus 9. How are we on time? 1/3, okay. Combining fractions sometimes helps if you have separated fractions. Or if you have just one fraction, separating your fractions or splitting fractions may be helpful. Using your even and odd properties of your trig functions. Remember, cosine was even, sine and tangent were odd. Even meant that the negative internal angle can just be deleted. Odd meant that the negative inside just gets dragged outside. So refer to your old notes for that. Something else that can be helpful. When you have separated fractions or maybe even just one fraction, if the bottom has got multiple parts, multiply top and bottom by the conjugate. I can spell, I promise. I just can't type well. Actually, the actual fact there is exactly the opposite of that. I type quite well and spell terribly, but just that word I know how to spell and was just making boo-boos. So by the conjugate, so you should have practiced that technique over and over in Pre-Calc 1 when you had something like 1 over 5 plus 3i, you multiply top and bottom by the conjugate of the bottom, which would have been 3. I don't remember what I said. Let me start over. 1 over 3 plus 5i, its conjugate would be 3 minus 5i. If you just have a fraction equal to a fraction, you could cross multiply. That might be helpful. Maybe one side looks really, really, really difficult and you don't even know where to start. So maybe you just try one side and then both sides eventually. And very often, I know that this is the technique I've probably used more than anything else in the grand scheme of things. Start over. Sometimes you're going to hit a dead end and you just got to start over and use a different technique along the way. Now, it could have been because you made a mistake, which would be unfortunate, but quite often it's just you're not seeing the way to approach. Now, here's the thing about these trigonometric identities. One problem could be done maybe 4 ways, maybe 9 ways, maybe 17 ways, maybe 27 ways, or maybe just 2 ways. There is a lot of variability with these. Some of the examples that you'll see me do next class, you'll see me do them more than once to prove the point that it's not absolutely do this or absolutely do this. And I didn't say that this is any kind of order. It's, okay, yeah, this thing might help you. Maybe another student doesn't like doing it and they manage to just use this middle Pythagorean identity and get away with the problem from there. So I believe that every example I'm going to be giving you has at least one alternative method, several of which I will show an alternative method. Some I won't. Just kind of once we get to the point of, all right, you've seen this enough, we got to do, we can't just spend 5 days on verifying identities. But pencil paper, this is something a lot of people don't like doing because it feels like, oh, it's the perfect storm blend of trigonometry and algebra, and it really is. You've got to know all these little pre-calc things. You've got to know, for pre-calc 1 things that is, you've got to know all your trig. If you're missing a single Pythagorean identity, you might not be able to solve one. I will tell you that my favorites out of this list are turn everything into sine and cosine. I do that 98% of the time for my problems. When you do that, you don't even have to know these other Pythagorean identities because you're only going to see sines and cosines, so you really only have to know that one. Remember that I said you can also, instead of memorizing the second and third, develop it by dividing by sine squared or cosine squared on both sides of the first equation. Factoring, definitely important. Combining fractions isn't necessarily my favorite, but splitting fractions I find can be helpful. And then starting over, those are probably the four that I use the most of, but I'm not saying I won't ever do any of these things. You will definitely see me do some of these things, if not all of them. Back to 6.1, verifying trig identities. So we said trig identities are equations that you must make the left and right side match. You will do this by using various trig properties seen in the last chapter. An identity is only verified once the sides match. Now, in the homework and the test, this feels a lot less traditional. It's another one of those cases of I really much prefer just blatant paper pencil versions of this stuff. But for simplicity's sake and not being face-to-face, we're dealing with what we got to deal with. So then my math lab homework tends to drag you more by the nose, and it gives you like the 4 steps and what they kind of look like with just certain pieces missing, and they'll give you a drop-down menu over what thing you should do to make the next thing happen. Like, should you use a Pythagorean identity, or should you use even odd properties, or should you turn everything into sines and cosines? What do you think? That kind of idea. So that's what the homework problems will look like, and that's what the test problems will look like. However, for the major, or for the more important major understanding of the topic, I'm not going to do my problems like that. I'm going to teach them the traditional way, the way that you should understand how to do them, because this stuff can creep up when you're in calculus every now and then. But it really stresses the importance of knowing your Pythagorean identities. That, you know, we don't really like things most of the time unless they're in sines and cosines, so that's a common way to simplify them. Factoring, the various different methods for factoring, so that'll come back in an even more complicated form. Combining fractions by getting an LCD, splitting fractions. Clearing fractions is an option I don't actually have up here, but it is a good option. Instead of combining fractions, you could clear fractions, which means multiply all the tops by the entire LCD. Use your even and odd properties. So cosine is even, sine and tangent are odd. So if you add a negative inside of one of them, you generally end up having to pull it out using one of those 2 properties. If you have a fraction that you just have no idea what to do with, maybe it's the only fraction, maybe try multiplying top and bottom by its conjugate. Cross multiply if it's just one fraction equal to another fraction. Try and just handle one side instead of both sides. Now this one right here, this is really what the homework and test problems will kind of emphasize, really only focusing on one side at a time. And then we said starting over is an unfortunate just side effect every now and then that we have to deal with. We might hit a dead end, or it might just be something we don't know how to handle and we need to try a different approach. So starting over, I cannot tell you how many trig identities I have started over in my lifetime. More so as a student, but as a teacher, it still happens every now and then. Nobody's perfect. All right, that's all we have there. How much room? We got a decent amount of room. So these basic tips, make sure you have all of them down. You can even throw in that extra one I mentioned, which was clearing fractions. And I'm not writing down all the, and I say this lightly, baby algebra, like what you do with your LCD and all that stuff. You should know that. That's why we're pre-calculus students, not algebra 1 students, or not even arithmetic students. Okay. Example 1, sorry, I don't know why that just happened. Example 1, verify. The only instruction I'm given, verify. And for this one, we're going to do cosine squared of theta, parentheses 1 plus tangent squared of theta, equals 1. So this is a trigonometric identity. The left side and the right side are identical. Believe it or not, that left side is equivalent to 1. Now, you probably don't automatically see that. I know I automatically don't see that. So we've got to take a couple of simplification steps to show that. Kind of like if you add x squared plus 5x squared plus 6x squared, you'd have to add the 1, the 5, and the 6 to get a 12, and then you'd simplify to 12x squared. That's the point of this. The point is not just making the left side match the right side. The point is, later when you're in calculus, if you have something like just this, that you would say, all right, well, let me try some trigonometric manipulations to see if I can just make it look a little prettier. And it turns out you can. It turns out it would be 1. That's the ultimate point of this. All right, so verify. What can we do? Well, I'm going to try, I see tangent squared, so some people might say we'll turn that into sines and cosines. I will do that in the next version of this example, though. I really think it's important that you do have these 3 properties in your heads at all time, because you might see variations of them or things that you can simplify with them. So in fact, one of them is up here. 1 plus tangent squared is the same thing as secant squared. So maybe applying that Pythagorean identity would be helpful. So let's do, I'm just going to write some abbreviations, Pyth for apply a Pythagorean identity, particularly the middle one. 1 plus tangent squared is secant squared. But Mr. Beckner, the 1's written in the wrong order. Oh, you silly student, you should know that addition order doesn't matter. All right, so the 1 plus tangent squared in blue, I'll show what I'm changing to. I'm changing it to secant squared of theta. And like I said, usually when I talk, I don't say the angle, but make sure you do write it. Everything that didn't change, I'll stay in black. Cosine squared of theta, and then equals 1. And this is, of course, at times if you need to show that. But if you don't put that dot, when you have a trig function sitting next to another trig function, it does imply multiplication. You could be really tedious and wrap each in parentheses, but that's just overly silly in my opinion. All right, so cosine squared times secant squared. What could we do next? Well, there's a few things we could do, but I would say the easiest out of this list, I'm trying to keep the list up here as best I can. Maybe if I zoom out a little. There we go. Turn everything into sines and cosines. Now, that was the thing I said we'll do in the next example first, but this time I'm going to do it second. So the first thing we applied was a Pythagorean identity. Now I'm going to turn everything into sines and cosines. And no, I'm not writing tangent there. I'm just saying I'm expressing everything in terms of sines and cosines. So the cosine squared I'm not going to change because it's already in sines and cosines. This, the blue ink, I will be changing. Please keep, go ahead, but in the future, keep questions in the chat. I appreciate that.
Oh, sorry.
No, it's okay. Go ahead.
Couldn't we just divide the left side by cosine squared and the right side by cosine squared and get the Pythagorean identity there?
That would be the reciprocal definition of cosine or secant, whichever you prefer. But yes, you right there have shown the point I made at the end of last class and what I will be doing today, that there can be 10 or 20 different ways to verify each of these. So that was an excellent point. So what was mentioned was that we could just divide both sides. I'm going to erase this after I do it, by cosine squared. And what you would get is that the secant squared is equal to 1 over cosine squared, which 1 over cosine is secant. So that would be secant squared equals secant squared. And that's when you would be done. So that is an excellent observation that would get you full credit on the test. But like I said, I have just a couple of particular ways I'm going to be doing these, but I do encourage open thoughts and thinking outside of the box, all that normal stuff. All right, so we're just going to change the secant squared to, well, secant we just said is 1 over cosine, so secant squared would be 1 over cosine squared. Oops, wrong color. So again, blue for what's changing. So this would be times 1 over cosine squared of theta. Then we have our equals 1. Now, again, in terms of formal proofs, this is not done because you haven't shown the cancellation. You say, oh, cosine squared in the top, cosine squared in the bottom, and what that gives you is, whoops, those cancel. Now I'm going to erase the cancellation, and that just gives us a 1 on the left side because everything else is gone. So 1 equals 1, and this is when we are done. The left side and the right side match. If you were going to go further down the road in math, what you might see a lot of people do is they'll write QED. This is Latin. I'm not going to spell it because I'll misspell it, but it's quod erat demonstratum, which literally means, translated, that which was to be demonstrated has been. Quod erat demonstratum. It just says, we demonstrated what you said to do. We did what you asked. We made the sides match. But a lot of times when you talk about proofs in math, they love QED. QED means you're done. You finished it. Everything's accurate. Now, what a lot of fake mathematicians, I'll say, might like to do is they'll, just fudge point something somewhere, and, oh, well, yeah, sure, this is that, and then it's done, and then write QED, and they say, well, since I wrote QED, it's done and it's accurate. But then someone goes in and goes, well, no, what you did here was wrong. It's not actually wrong. I'm just saying someone would do. That was right, so don't misthink there. But that's what an official verification looks like. This is one of the many, 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 many different ways this one could have been done. The downside of the technology here is, while there's really about 20 different ways to solve this one, to verify it, not solve, my math lab is going to take you through one specific type. So they'll probably do this and then that, or maybe they'll do it as the alternate approach I'm about to take. So an alternate method, so which we already went through one and erased it, where we divided both sides by cosine squared, or we could have divided both sides by secant squared. There's all sorts of different things. You could inject Pythagorean identities from there if you really wanted, but it would just take the problem 5 times as long to do. All right, so the first time I did the Pythagorean, then I did the sines and cosines. But the problem there is a lot of people don't remember that this is secant squared. So if you were a student who forgets that secant squared, maybe instead of doing Pythagorean first, maybe you switch to sines and cosines first. So we have our, all right, cosine squared times 1 plus tangent squared equals 1. So I'm going to switch to sines and cosines. Let me zoom back in, so I don't have to write so teeny. So the cosine squared is fine. I'll leave that alone. But the 1 plus tan squared is going to become 1 plus sine squared over cosine squared. If tangent sine over cosine, tangent squared is sine squared over cosine squared. And by the way, I'm not trying to discourage anyone from asking questions earlier. If you have to ask that way, that's fine. But I do just ask to try and keep them in the chat. Again, not discouraging questions. I appreciate them. Okay, so, well, now what you could do is you could distribute if you wanted to. That would be one thing to do. So this cosine squared, you could give it to both terms inside. Just an algebraic simplification potentially. So cosine squared times 1 would be cosine squared. That's supposed to be blue. And then distributing the cosine squared to this fraction. I know this might be confusing, but this cosine squared is this cosine squared. Now the one that was originally a fraction, I'm going to write in black. So this right here is this. I'm going to erase the circles in a second. Remember I said the blue I was trying to keep to the new thing, so that was the distribution. All right, erase. Go. All right, well, this right here, cosine squared times sine squared over cosine squared, you can cancel. There's a cosine squared in the top and in the bottom, kind of like there was over here. So those will cancel each other out, which I forgot to write the word cancel last time, cancel. So that's just going to give us cosine squared of theta plus, now that's just a sine squared of theta. And yes, I know sometimes my thetas end up looking like 2s. Please forgive me. And then what happens here? A lot of students on a old school paper pencil test, they'll stop here and they'll say QED. Oh, I said QED, I'm definitely done. And then they get their test back and they've lost a couple points because that's not right. Yes, it is true that cosine squared plus sine squared is 1, but you haven't verified it. You verifying it means you need to write the left side. You need to use your Pythagorean identities that sine squared plus cosine squared is equal to 1. Now we see the left side match the right side. Now we're done. Now we can say QED. That which was to be demonstrated has been. It doesn't mean that the answer or the final equation has to be 1 equals 1 or 2 equals 2. It could be sine squared plus cosine equals sine squared plus cosine. That would be done. Excuse me for a second. All right. So 2 ways. One of them involved a distribution, but both of them, well, the other one didn't. Both of them ended up using Pythagorean and sine cosine and some kind of canceling. It's just a different order and a different Pythagorean identity. This Pythagorean identity, that was weird. This Pythagorean identity is one that people tend to know less, but you should still know. This Pythagorean identity is one that everybody knows, or I don't know how you pass this class without knowing that. It might be possible. So many different ways to get these problems done. Now, some problems are really bad, and it seems like there's only one easy way. But that doesn't mean there's only one way. It just means there's only one easy way. So again, I don't really like the fact that the homework, again, drags you to one particular way, but at least it is detailed enough for you to follow. And I give lots of examples so you'll see all the different variations they could do to you. All right, B. Cosine squared of theta minus sine squared of theta is equal to 2 cosine squared of theta minus 1. So you might say, oh, the left side's 1, right? The left side's 1. Well, no, that would not be right, because that's not sine squared plus cosine squared. It's cosine squared minus sine squared. What's interesting is that's actually another identity we're going to learn later, but not quite yet. So there's a couple things you could do here. I'll describe some things that I'm not going to write down, at least for the first run. I could move things from side to side. This is an equation. Nobody said you can't move things from side to side. So maybe you move the cosine squared to the right, or the 2 cosine squared to the left, or the sine squared to the right, and the 1 to the left. I mean, you could do all sorts of different things to this in an attempt. But for now, I'm not going to do it that way. Again, I'm doing some of these 2 ways, so maybe I'm going to do it the second way. The first thing I'm going to do, and it's not super obvious, I'm going to do a Pythagorean identity. You go, how are you going to do that, Mr. Beckner? The Pythagorean identities are these 3 things. Obviously, we can't use either of those for this example. It's got to be the first one. But the first one says sine squared plus cosine squared equals 1, and you just said, Mr. Beckner, that that's cosine squared minus. It's a minus instead of a plus, so how are you going to use a Pythagorean identity? This is how. You only change your cosine squared or the sine squared, which means you're going to have to rearrange the Pythagorean identities. So here's the first variation. Sine squared plus cosine squared is equal to 1. Or, and I'm going to erase the algebraic step, what you could do is subtract cosine squared on both sides. When you do that, you'll only have the sine squared on the left, and on the right you'll have 1 minus cosine squared. Actually, I won't erase it. So you get sine squared of theta is equal to 1 minus cosine squared of theta. So this is an alternate form of that Pythagorean identity. Or if you took the sine squared of theta plus the cosine squared of theta is equal to 1, you could instead subtract the sine squared on both sides. Again, sorry for the thetas that look like 2's. And you get cosine squared is equal to 1 minus sine squared. That's the other variation. So if you see a 1 minus cosine squared, you could turn it into sine squared. Or if you saw a sine squared, you could turn it into 1 minus cosine squared. Or if you saw cosine squared, you can write 1 minus sine squared. Or if you saw 1 minus sine squared, you can write cosine squared. Now, I said to only change the cosine squared or sine squared. So what I'm saying is you're either going to use this one or you're going to use this one. Now, technically, big surprise, doesn't matter which one you use, but there's an easier way out of the two options. The easy one is to replace the one that there's less of. So I have a cosine squared twice here. There's 2 of the cosine squares, but there's only 1 of the sine squares. So it is my opinion that replacing sine squared would be easiest. Did not say it's the only thing, it said it's the easiest. So we're going to replace this sine squared here with 1 minus cosine squared. Now you might be thinking, well, Mr. Beckner, you just gave me 2, arguably 4 more different formulas to memorize. How many formulas are you going to give me to memorize by the end of the semester? No, I didn't. I gave you a formula that I manipulated algebraically. The same idea, how we took sine squared plus cosine squared and turned it into the formula with tangents and secants or cosecants and cotangents. Algebraic manipulations. So you can memorize or you can manipulate. It's up to you. Pick your poison. All right, so the cosine squared, I'm leaving alone. And the minus, I'm not changing the minus, but the sine squared, I'm changing to 1 minus cosine squared over here. What I'm writing is wrong, what I'm writing is wrong, what I'm writing is wrong, what I'm writing is wrong temporarily. Because this minus was applied to the whole sine squared, which is this whole thing. You guessed it, we need a parentheses. Very easy to miss. Equals 2 cosine squared of theta minus 1. Now what we can do is distribute on the left. The minus in the parentheses, I mean, it just seems like nobody's going to want that, so let's distribute it. So we get cosine squared of theta. That's now a minus 1 and a plus cosine squared of theta. The right-hand side I have not changed. It's pretty common that we only deal with one side of the equation, but you can choose to manipulate them and move things. Like I've said, we'll do that next, in the next version of this example, that is. All right, we got cosine squared minus 1. We got cosines, and then plus cosine squared. Cosine squared and cosine squared are like terms. It's apple plus apple. Apple plus apple is 2 apples, so cosine squared plus cosine squared is 2 cosine squared. So all we did here is combine like terms, CLT, combine like terms, blue, which gives us 2 cosine squared of theta. The minus 1 is not changing, so it's back to black. I'm not changing the right side at all. I haven't this whole time. I could have, but holy cow, the left side matches the right side. We're done. QED. So I chose to take what I think is the easier method of just replacing something once. Although a lot of people might go, I do not like this minus there. I know I make that mistake all the time with the distribution. So I'm going to go against your grain, Mr. Beckner, and I'm going to replace the cosine squareds. Okay, fine. So the left side, this cosine squared would be 1 minus sine squared. So you'd have 2 negative sine squareds, which would make a negative 2 sine squared. This on the right side, the cosine squared would also become 1 minus sine squared, but there's a 2 in front of it. So you'll have a negative 2 sine squared, and then a 2 and a minus 1, which would make a 1. And everything works out perfectly. Here's the alternative way, though. So I just described an alternative way, but here's a drastically different way. So cosine squared minus sine squared equals 2 cosine squared minus 1. Let's just rearrange. I'm just going to move some terms. Move things. How? Well, I see sine squareds and cosine squared, so maybe I try and move all the trig terms to one side and all the non-trig terms to the other side, because then maybe I can make it look like this. Maybe I can make it look like that by algebraic rearrangement. So that's a -1, so I probably want to move that to make it positive. Don't have to, there's a workaround for that. So let's add 1 to both sides. Then, all right, we have a single cosine squared on the left, but the ones on the left now, we don't want that. We don't want the trig term on that side, so let's move that. Let's subtract cosine squared, like that. And then the sine squared, we're also going to need to move to the right. And you can show this in several steps if you need to. And after you do that, so we have the 1 on the left, the cosine squareds cancel. The sine squareds cancel. So then we just have our equals. 2 apple minus apple is 1 apple. So 2 cosine squared minus cosine squared is 1 cosine squared. I'm not going to write the 1 in front though. The 1's canceled. We have this plus sine squared. And yeah, that is the Pythagorean identity right there. But you're not done. You need to change the right side to be just 1 by Pythagorean. And you're done. QED. Some of you will think the second version's easier. Some of you will think the first version's easier. Some of you will think the first version, but replacing the cosine squares instead of sine squares will be easier. There are so many variations of this problem. I could probably take 45 minutes and just keep doing the same problem. But that would be boring, and we don't have that much time together, as you know. QED. C. Oh, and I wanted to, well, no, I don't. You'll see it. You'll see it. Cosine of theta times cotangent of theta is equal to 1 minus sine squared of theta over sine of theta. All right, so my brain, the way I do things with this is I generally tackle Pythagorean and turn things into sines and cosines first. If I don't see a Pythagorean identity screaming at me right now, then I turn everything into sines and cosines. Or I can just go ahead and turn sines and cosines and still maybe see a Pythagorean identity. Just depends on how you want to approach things. I can manipulate just the left side, I can manipulate just the right side, I can manipulate both. So I'm going to do sines and cosines first. So let's just turn everything into sines and cosines first. That's going to be my choice. And that does not say tangent, that's just me making a little memo that we're changing things to sines and cosines. Well, cosine of theta is cosine of theta. That doesn't change. Cotangent does though. Tangent sine over cosine, which means cotangent's cosine over sine. So that's a change. There's no tangents, cotangent, secants, or cosecants on the right, so I'll leave it alone for now. I will say technically there's a Pythagorean identity in there, kind of just how we were doing in the last example, but I don't want to do too many things at once. All right. Well, cosine times cosine on the left is cosine squared, so you could just say simplify, stack, whatever. So the left now, the top changes to cosine squared. The bottom is still sine of theta. Again, blue for what changed, black for what didn't change. And that's 1 minus sine squared of theta over sine of theta. And even from just this point alone, from this point to finish it, which could be done in probably about 1 to 5 steps, depending on your path, I see at least 10 different ways that I could verify this. Notice one thing, the bottoms are the same. Since the bottoms match, all we really need to do is just focus on the tops, since the bottoms match. We can just focus on the tops since the bottoms match. If the bottoms are the same, that means the tops have to be the same. So cosine squared equals 1 minus sine squared. Again, all I'm focusing my energy on now is just these two things, trying to make them equal. Well, I see sine squareds, cosine squareds, and 1s, so it's probably a Pythagorean identity. So you can memorize the variations, and here's the cool thing about those two variations we just established, these two asterisks. It's always one of them squared is 1 minus the other squared. Sine squared is 1 minus cosine squared is 1 minus sine squared, and that's just because of the simple algebraic rearrangement. When they're on the same side, it's positive 1. When they're on the other side, one of the trig functions has to be negative. So we're either going to use this one or this one. Well, I see cosine squared and 1 minus sine squared, so it's definitely this one. Now I can choose the left side and replace it with the right side, or I can choose the right side and replace it with the left side. There's two options. Doesn't technically matter. So it's Pythagorean. I'm going to replace the left side. A lot of people like to just replace the single term. So I'm going to replace the cosine squared with, what did we say it was? 1 minus sine squared. So 1 minus sine squared over, bottom didn't change, sine of theta. And I'm not changing the right side at all. You don't want to change the sine squared into 1 minus cosine squared in there. You don't change both. You want to have just one of them. If you see a mixture of cosines and sine, a mixture of cosine squareds and sine squareds, just change one of them over, not both. And then over the sine of theta. These are literally the same, so you are done. So alternatively, in orange, because this is completely different, when we were at the cosine squared of theta over sine of theta equals 1 minus sine squared of theta over sine of theta, some people will choose to replace the 1 minus sine squared with cosine squared. So that's the replacement I'll do this time. So blue for what changed. So that would be cosine squared of theta, and then you're done. Some people would have said, oh, you have a fraction equal to a fraction, so cross multiply. Sure, that can get you the answer as well. I'm not going to show all the work for that, though. Some people would have cleared the fractions. Some people would have done, all right, well, I got 1 minus, sorry, not that. We got cosine squared over sine equals 1 minus sine squared of theta over sine. Some people would have said, all right, I've got an LCD of sine of theta. So they multiply both sides by sine of theta, wrapping the top in the parentheses because you have to, so that you see the denominators all go away. No more fractions makes the problem a little easier on the brain, right? Oops, too far. There we go. And then what we end up with is cosine squared of theta equals 1 minus sine squared of theta. Then you could literally do the same replacement of the left or the right hand side, or you could take an alternate approach and add sine squared of theta to both sides. It looks like 2 theta, not squared. Doing that gives you sine squared plus cosine squared equals 1. And then you're done. As I said, most of these problems have countless ways to verify their identities. The homework kind of forces you into one particular way, but at least it's just a drop down and like a 4-option kind of thing. It's not too bad. It really isn't too bad. It, in my opinion, makes it too easy. which is why for the next test, I may have like a paper pencil submission problem for a couple of these by themselves, thinking about it. All right, sine of theta over tangent of theta. Then plus cosine of theta over cotangent of theta is equal to sine of theta plus cosine of theta. And again, the real point of all this is that way when you're in calculus and you've got this thing on the left-hand side and it looks like a mess, ultimately you understand that you can simplify it to be something prettier. And maybe you don't know that you can, maybe you're just trying. And then in trying, hopefully you didn't end up with it. Because trying to do calculus with sine over tangent or cosine over cotangent, I don't know how to apply those calculus formulas to that, but I definitely know how to apply the formulas to sine and cosine. So it's very often about cleanup. All right, so there's a lot of things going on with this. There's a lot of different paths. And what's interesting is that most of the paths you'd end up using in LCD because you see fractions, you see denominators. And with a denominator of tangent and then another denominator of cotangent, the LCD is tangent times cotangent. So that's one way you could do things. And I'm going to do that as the alternate method. And what's interesting is that LCD is a lot more simple than it looks. How do I want to do this? I'm trying to decide if I want to clear the fractions or leave the fractions. But we're going to turn everything into sines and cosines first. So that's what we're going to do. Sines and cosines. I don't like looking at all these tangents and cotangents. Let's get rid of them. So that's what one student will think. And if they don't think it initially, they'll probably think it in a little bit of time later. All right, so blue is going to show it changes. So we got sine of theta over, instead of writing tangent, that's sine over cosine. And the plus, we have a cosine of theta all over. And instead of writing cotangent, we're going to write cosine over sine. Leaving the right-hand side alone. All right, so this is division of fractions. The black over the blue is division by a fraction. So let's multiply by reciprocals. So change to multiplication by reciprocals. Remember that A over B on top of C on top of D is the same thing as A over B division symbol C over D, which is A over B times D over C. So dividing by the blue is the same as multiplying by flip the blue. So we'll have sine of theta, here's what changes, times cosine of theta over sine of theta. See, this division became a multiplication and we flipped it. That is old school arithmetic, but just with trig functions in place of numbers. Then the cosine of theta from the very top, now we change that to a times, flip the cosine over sine to a sine over cosine. Equals sine of theta plus cosine of theta. Well, simplify. Sine times sine. Sorry, sine over sine, gone. Cosine over cosine, gone. Wow, we went from a fraction to an even worse fraction to no fractions. How convenient is that? So now this first bit is just a cosine of theta. Again, these two things canceled, leaving just that cosine. Then the plus. Now here, the cosines cancel, leaving just the sine. Then the right-hand side, we have not touched at all. Now, this technically, if you really want to get ridiculously specific and higher math, this is not done because the left side and the right side have has a plus b versus b plus a. Nobody cares in trigonometry though this is done. This is verified. QED, finito, whatever. Mic drop.
All right, so we're going to call it a day at that point. Actually, before I talk about this, when we come back, we're going to do this problem again, but we're going to do it an alternate way. If you remember when I was introducing the section that most, if not all problems have an alternate way that they can be done. I prefer to say most because I'm sure there's a problem out there that can't be done in our class at our level an alternate way, but generally all the problems I give can be done multiple ways. Anyways, we will do several problems a first way and then an alternative way, not to say one is regular or the other is, just showing how we can arrive at the same conclusion by two or more paths. So yeah, besides that, we know that 5, 5, 5, 6 are due. 5, 7 is due on the 22nd, 5, 8 the 24th. We have our test the 24th or the 25th, whichever day you prefer to take it. I will not be accepting late work for this test unless you have some kind of medical documentation, something like that. So please, please, please make sure you take that test. We don't want any bad grades just because of missing the test or forgetting. And the review is available already. And then a week from today, I will not be holding class on Zoom. Everything's going to be pre-recorded. You'll just find the YouTube links available in, that morning, probably no later than 8 a.m. instead of the usually like 2 o'clock when I get everything done here. All right. So besides that, have a good day. Have a good weekend. Start studying for this test since it's in a week. Email me if you have any questions per usual, and we'll see you on Tuesday.